So, we continue in this particular lecture and we discuss the other side of the inequality, where we try to see that L bar is less than h x plus 1. That means, the minimum value of the expected code word length is at most deviating by 1 bit more than the entropy. So, we move further, and what we say is that we would like to show that prefix free codes exist for L bars with h x less than 1. So, if we can show that prefix free codes exist for this particular setup, then we can of course say that since L bar min is less than or equal to L bar, then of course we can find prefix free codes which satisfies this particular condition. To do so, we would say that you start off by choosing the code word length L j, which is equal to the ceiling of minus log base 2 of p j. So, where we could write the ceiling function, it denotes the smallest integer greater than or equal to u, right, that is well known. So, what we know is that we can write that minus log base 2 of p j. From this we can write, or L j lies between this on the lower side and on the upper side minus log base 2 p j plus 1. So, that means, from this it is either equal to this or greater than this, and it is less than this particular number. Now, when p j is an integer number, integer power of 2, of course, this holds with equality, and of course, this is also satisfied. So, when we look at this particular part of the inequality, we can write that log of 1 by p j is less than or equal to L j, and therefore, we can say that 1 upon p j is less than or equal to 2 to the power of L j, or in other words, that would also suffice to mean that p j is greater than or equal to 1 upon 2 to the power of L j, or you could also say that p j is greater than or equal to 2 to the power of minus L j, right. So, we have arrived at this point from this definition, and if you take summation over L j on both the sides, what you have is summation of j from 1 to m p of j is greater than or equal to summation of j from 1 to m 2 to the power of minus L j. So, this, since it is a probability space, it is 1, and this side is j equals 1 to m 2 to the power of minus L j. So, what it shows is that these code word lengths, if chosen according to this, satisfies the Kraft inequality. Now, since it satisfies the Kraft inequality, what it implies is that these set of lengths that we have started with, these set of lengths, it can construct prefix free code words. So, that means, if we take these kind of code word lengths, which we have selected from the previous solution, where we have minimized the code word lengths by taking the Lagrangian and hence taking the derivative, we have found that L j is equal to minus log of p j, or log base 2 1 upon p j, and that was for real lengths. And then we said, if you have to take integer lengths, you can take this ceiling function, which is the nearest integer. So, even by selecting that, we can say that one can find these set of code word lengths would satisfy the Kraft inequality. That means, you can construct prefix free codes. So, that is the first constraint that it satisfies. Now, we move down further and we try to see what do we have with us now. So, in other words, what we have to summarize, that you can construct prefix free codes with this. All right. So, moving further, So, if you take the RHS of this, that means Lj is less than or equal to minus log base 2 Pj plus 1. Since we have this, then we can say that L bar, which is the expected value of code word lengths, by definition it is sum of Pj times Lj. So, since Lj is less than or equal to this, you can say that this is less than or equal to sum of Pj. Of course, this is sum over j equals to 1 to m. I am not writing it because it is repetitive, minus log base 2 of Pj plus 1. So, if you take this particular summation, what you have is sum over Pj log base 2 Pj with a minus sign, which is Hx or the entropy as per definition, plus summation of Pj multiplied by 1, that is summation over Pj over the entire set is equal to 1, and hence what we can say is that L bar is definitely less than or equal to Hx plus 1 simply by taking the right hand side of this, and that because we have taken code word lengths of this. So, what we have shown is by taking code word lengths which are integer nearest integer to the solution of the Lagrangian, you can find code word lengths which satisfy the Kraft inequality, that is by taking the left hand side of this, and by taking the right hand side of this we have come up to the point where we say that the expected code word lengths are at most 1 bit more than the entropy. Now, since L bar min is less than or equal to L bar, therefore, we can clearly write that L bar min is less than Hx plus 1, and hence we have the full set of thing, that is Hx is less than or equal to L bar min, which is less than Hx plus 1. So, this establishes the entropy bound on L bar min. So, that means what we can say in summary is that if you choose code word lengths according to this result, which was due to the Lagrangian that we have derived in the previous lecture, that you take the Lagrangian of the summation and with the constraint that it satisfies a prefix free code, that means it is a Kraft inequality. We ended up with a solution without the ceiling function. So, when you ended up with this particular solution without the ceiling function, you have real solutions, real lengths, and we said when this probability are integer power of 2, you have the exact solution for which it is the minimum. Now, when it is not integer power of 2, you can take the ceiling function to take the nearest integer, which is greater than this particular number. So, even by taking this solution, we can find that these lengths would satisfy Kraft inequality, as we have seen over here, and not only that, those lengths would produce an L bar which is at most 1 bit close to Hx, and that is because of this right hand side. So, all it tells us is that we can select these set of lengths given a set of probability, and once you do that, you have already found an L bar which is the best solution of the average code word lengths that you need to choose. So, in other words, you can say that L is approximately equal to log base 2 of Pj, or a better way to say is that this length j is equal to the ceiling function of minus log base 2 of Pj. So, if it is an integer power of 2, Lj is equal to the number inside the ceiling function. If it is not an integer power of 2, then it is the smallest integer lesser than this. So, there is of course one particular example which you can take to show that things are not quite so straightforward. We will just do it just for the sake of example. Suppose I have zeros and ones coming out, and let us say I have the probability of a 0 being equal to 2 to the power of minus 10, and probability of 1 is 1 minus 2 to the power of minus 10. So, going by this, we find that the number of bits I should put to 0 is 10, and according to this will be the number of bits that I should give to 1, and definitely what we see is that this is not the one which is going to minimize the average code word length. So, why is it so, and what are the things fallouts of it, and what can be done even to make it very close to entropy is something what we are going to see very soon. So, before we proceed with the particular details of example, would like to remind that when we did when we did fixed length codes, we had taken a set of source symbols. Let us say there be 5 source symbols, for example A, B, C, D and E. If I have to give fixed length codes, we said that since this is 5, 2 bits will not help, because 2 bits would create 4 options. So, you need to take 3 bits. So, every symbol are going to get 3 bits, right. So, if you do this, you would be not doing it very efficiently, because with 3 bits you can encode 8 symbols, but here you have 5 symbols. So, there is a bit of wastage, and then we found that probably you can make things better if from this source, which produces a sequence and so on, instead of encoding one symbol at a time, if we group a few symbols, let us say we have taken 4 groups, and we create a super symbol. So, that means if I select n symbols, in that case if I select n symbols, and if there are m symbols in the constellation, so what I have is 1, 2 dot dot up to n. That means each position can be taken in m different ways. So, overall if I group these symbols, I can say that this is a new symbol, and then we can ask how many possible new symbols do we have, and the answer is m raised to the power of n. And now, if we encode this particular symbol, what we can say is that we can be 1 by n close to the best possible situation. So, by making n very very large, you can reduce the overhead in this case, or the losses in this case. So, we will extend that same philosophy for variable length codes. However, when you have to do it for variable length code, one have to use the calculus of entropy. So, what we are going to do is we are going to show the expression of h x y. So, if you have h of x y, where x and y are 2 different random variables, so this could be defined as sum over p over the joint distribution of x and y times log of p x y of x y by the same definition. Of course, it is log base 2, and if x and y are independent. So, if x and y are independent, so remember we have taken discrete memoryless source. So, when we have taken discrete memoryless source, in one of the postulates we said that the outputs are independent and identically distributed. So, that means 2 symbols that come out do not have memory. So, that was the memoryless source. So, here we are talking about the sequence which takes 2 symbols. In this case, if it is IID, we can say they are independent. So, this joint distribution becomes a product distribution, and of course, this is over the set of x and y. So, we take the Cartesian product for all combinations of x and y, or over the whole set of x over the whole set of y. So, what we have is p of x times p of y log base 2 p x of x. Since it is a multiplication, inside the log we have this summation right. So, if you take this first product, what you have is p x times this times p y, and since this is over x times y, we would first add up through all of y, and what we have is p x, I will write in short log p x, here p y, summation over y, summation over x. So, when this is added over all y, since these are independent, what this leads to is summation over p x log of p x times summation over p y over all of y, which would lead to summation of p x log p x, and this would equal to 1, right. So, we use that, and what we have is this is equal to of course, there is this minus sign h of x. Similarly, when we apply to this, the summation over x becomes 1 and we are left with the y terms. So, get h of y. So, for independent sources, in general one could write that h of x n is equal to n of h of x, because if we now take x, x, x and x, or x 1, x 2, x 3, x 4, and we call it x to the power of 4 because we have taken 4 symbols, we are going to get h of x or h of x 1 plus h of x 2 plus h of x 3 plus h of x 4, and if all of them are identical, what we have is h of x plus h of x plus h of x plus h of x. So, what we have is 4 times h of x. Now, if you generalize it and you say that I want entropy of x n, that means n length sequence where all of these are independent, we can write it is h of x plus h of x plus h of x up to n times. Instead, you can write n of h of x. So, since you have now got this, so we will now try to define what we are trying to intend at by or rather it is also known as what we are trying to do is fixed to variable length coding, fixed to variable length coding. You can take it under this particular heading as well. So, what we have is a block of n source symbols x 1, x 2 up to x n. So, we have this, and we say that this has entropy h of x n and since we have seen that h of x n is equal to n h of x n, we can say that such a block is a random symbol and can be encoded using variable length, prefix free code. So, what we have is a block of n symbols, source symbols. So, now we are selecting this block of symbols. So, it is a fixed length, and then we are saying such a block can be a random symbol, which we have already explained. For example, if you are taking a very basic source as 0 and 1, now instead of taking one symbol at a time, encoding a 0 and encoding a 1, you can think of encoding a sequence, and let us say 2 bits, and we take whenever there is a 0, I would encode it as a certain symbol. Whenever there is a 0 1, I would encode it at a certain symbol, and so on and so forth. So, I would take 0 0 as my new symbol. I would take 0 1 as my new symbol, and so goes 1 0 and 1 1. So, in this new case we have 4 symbols. and we would like to encode these 4 symbols which have come from the original source. You could have taken 3 bits, and in that case 000 could be one symbol, 001 could represent another symbol, and 111 could represent another symbol. So, that means that we now have a source which has 16 symbols. Previously, there was a source which had only 2 symbols, and now what we are trying to do is encode these 16 symbols into a variable length coding. Now, the result is more or less well understood at this point. What we can do is, suppose I give probabilities of zeros and probabilities of 1. So, for example, if I say that 0 comes with a probability of, let us say, 1 upon 4, and 1 comes with a probability of 3 upon 4. So, when I have a 0 0 0, I can calculate the probability as 1 by 4 multiplied by 1 by 4 multiplied by 1 by 4, or in other words 1 upon 64 as the probability of this particular symbol. And the probability of this particular symbol is 3 upon 4 times 3 upon 4 times 3 upon 4. So, this has a probability of 3 by 4 multiplied by 3 by 4 multiplied by 3 by 4, which is 27 upon 64, and this has a probability of 1 by 4 times 1 by 4 times 1 by 4, which is 1 upon 64. So, now since we have this, we can recollect that we can use lengths which is equal to log base 2 of 1 upon p j and take the ceiling function of that, and that will give me the code word lengths which to be used to generate prefix free codes, which would be minimum possible lengths. So, you can keep doing this until the point, or as I make n large is the new result that is what we are interested in this particular discussion. So, here of course, what we say is L bar is the expected number of bits per original source symbol, and what we can say is that this can be made as close as possible. So, this can be made as close as possible to h x. This is what we are trying to see, okay, as desired. We have seen such a similar result in case of fixed length code. We will see the similar thing. So, here we say that let E of L of x n, this is to be understood as x n is the block of length n, L is the length of code words where the source symbol is made up of n original source symbols, and E is the expectation operator. So, what we can write is this is the expected length of a variable length prefix free code for x n, okay, and E of L x n min is naturally the minimum expected length of the same. So, what we have is that from the previous entropy bound, we can say h of x n is the lower bound on E of L x n min, which is less than h of x n plus 1. This is well known. Now, if I define that L min n or L bar min n to indicate that this is equal to E of L x n min upon n, that means the minimum number of bits per original source symbol over all prefix free codes. That means, look at this, this is the minimum expected length of code word for this block. So, since this block is created by n symbols, this divided by n would indicate the number of bits per original source symbol, right. So, what we have at this point is we extend, we go ahead with this, and we have this result is already established n h x n. So, instead of this we write this, and here this is equal to n times L bar min when taking n tuples at a time is less than, again the same result we would apply over here, n h x, this is a mistake, it should not be here, plus 1. So, clearly what we have from this, if we divide by n all over, what we get is h of x is less than or equal to L min bar when taken in a group of n tuples is less than or equal to h x plus 1 upon n. This is a very, very important result what we have arrived at, which tells us that by choosing appropriate lengths you can by choosing appropriate lengths. However, if you group n tuples, that means instead of taking one symbol at a time, if you take n symbols, you can make the minimum code word length per original source symbol as close as possible to h x, which is the entropy, which is the lower limit, as desired by taking n very, very large. As n tends to infinity, this number becomes very close to h x. So, finally, we can state the prefix free source coding theorem as for any desired memoryless source with entropy h x and any integer n greater than or equal to 1, there exists a prefix free code or prefix free encoding of source n tuples for which the expected code word length per source symbol L bar, denoted by L bar, is at most h x plus 1 upon n. Can also state further, no prefix free encoding of fixed length source block of any length n results in an expected code word length L bar less than h x. This is a very strong result which tells us that you can design code word lengths such that it is very much possible to bring it as close to entropy as desired, because entropy is the lowest limit to which you can achieve, and to make things best you can take blocks, and these blocks would be, if it is pretty large, you can make this coding scheme as efficient as possible. We stop this particular discussion at this point. We will continue on this topic in the next lecture. Thank you.